5 or 6 slides here in chapter 13. And I think there's just one more important reaction to cover, reduction. Okay, and that's good we started out there with oxidation, because we'll be able to see the contrast between oxidizing an alcohol to produce a ketone. We produced a ketone over there. If we had oxidized a primary alcohol, we would have produced an aldehyde. But here we produced a ketone. Does anybody have any questions about chapter 13 so far? Is there anything you're struggling with? Okay. All right, let's finish off this one last reaction. Yeah, and you can see going from an alcohol to from an OH to a carbon-oxygen double bond, whether it be an aldehyde or a ketone, you're oxidizing. Going from an alcohol, or to go from a carbon-oxygen double bond back this direction is reduction. That's what we're going to look at right now. Hydrogenation of this carbon-oxygen double bond. And it's really not the first time we've seen this. All right, here is your aldehyde. So I mean, really what you got here, this isn't just one reaction. This is kind of like an aldehyde if you had, so think of this as kind of two reactions. There's one reaction, there's another reaction. You have platinum there, platinum there. They're just saying same catalysts are used and the same reactant are used for this. So this one here just has 4 carbons. Let's put this hydrogen down here. And we're adding hydrogen. We've got our platinum catalyst or nickel or palladium. That's not suggesting you need all 3 of those. You just need a catalyst, and the most common ones are platinum or palladium or nickel catalysts. And just keep in mind, this is it's this situation where this is going to bind to that oxygen, this hydrogen is going to bind to that carbon. We're going to get rid of those 2 bonds, form 2 new bonds that way, and so we end up with an OH. Where we had an O, where we had a carbon-oxygen double bond, we end up with an OH, and we get an alcohol. And it is a primary alcohol. So the aldehyde produces a primary alcohol. Hydrogenation. If you go back to this slide, reduction is the gain of hydrogen. It's either the loss of oxygen or gaining hydrogen. Hydrogenation is gaining hydrogen. The molecule is gaining 2 hydrogens. We have only one here on the end to begin with, and we end up with one on the OH and 2 others right there. So we had 1, we end up with 3. We've added 2 hydrogens to that molecule, and this is reduction. Hydrogenation is reduction. All right, so the top reaction is the same thing. The same scenario is playing out with a ketone. We just happen to have a carbon-oxygen double bond along the chain, and so we end up with a secondary alcohol. We end up with an OH along the chain. So that the reaction of a carbon oxygen double bond with hydrogen is the same, whether it's an aldehyde or a ketone. The big difference is the type of product you get. Primary alcohol with an aldehyde, ketone with a primary alcohol with an aldehyde, a secondary alcohol with a ketone. So that's the important takeaway right here. Ketone plus hydrogen yields a secondary alcohol. A aldehyde plus hydrogen is going to yield a primary alcohol. Yeah, so there could be a question on the test, and it's not, the answer isn't just, oh, a ketone plus a hydrogen yields an alcohol. It's specifically what kind of alcohol, secondary alcohol. Well, let's see here. Yeah, let me give you, let's take this cyclohexanone. Let's take something that's a little bit more, hydrogenate that. What would be the result of hydrogenating cyclohexanone? Now that's not aromatic. Notice that's not aromatic. This is just a 6-membered saturated ring, and you've got a carbon-oxygen double bond on it. Okay, when you add hydrogen, one goes on the oxygen and one goes on the carbon that held that oxygen. That's where those hydrogens go. So, I mean, if you look at what you have here, you know, here's what you have. If I just kind of bring that out into the open a little bit. And so what you're going to get, you're going to get a hydrogen here, and you're going to get a hydrogen there. And I mean, there's the hydrogens here. There always was. We're not just, there always were hydrogens coming, 2 hydrogens coming off of here. There's nothing coming off of here. There's 1, 2, 3, 4 bonds. That's it. There's no hydrogen. But you hydrogenate that, you reduce it, and well, we've got 2 hydrogens down here. And you get this molecule. And what's the name of that molecule? Cyclohexanol. Cyclohexanol. This is a ketone. And we're getting a secondary alcohol. That's a secondary alcohol. It's not a primary alcohol. This is in the middle of a chain. Happens to be a chain that forms a ring. So that is a secondary alcohol. Remember, you classify alcohols. You look at this carbon. You say, how many carbons is it attached to? 1, 2. It's attached to 2 carbons. This makes that a secondary alcohol. Okay, so that's reduction. This next reaction, the hemiacetal reaction, you'll hear us make a big deal out of this in chapter 16 when we start talking about sugars. You have already seen a lot going on with double bonds. You can add hydrogen across a carbon-carbon double bond. What we just looked at is you can add hydrogen across a carbon-oxygen double bond. What are we doing down here? We're going to add something across a double bond, but it's going to be something new. Just kind of focus on this part of it here. We've got this carbon-oxygen double bond. And let's pick out an alcohol here. We're going to react an alcohol with an aldehyde. And let's pick out a real simple alcohol, which would be methanol. I'm just writing it in a kind of a different manner there. So all I'm doing over here, I just got this molecule here, which is methanol, right? You're familiar with seeing it this way. What am I doing? I'm accentuating right here this hydrogen-oxygen bond right here. There's nothing different here. I'm just saying let's really focus in on this hydrogen-oxygen bond. And this alcohol is going to add to this double bond in a very similar way that hydrogen adds to a double bond. Part of the molecule is going to go on the oxygen, and the other part of the molecule is going to go right here. All right, so if we had an aldehyde, where would we go with this? Well, let me go through let's go through an intermediate step here. We're going to have this going on. All right, so this bond is going to start going away. We're going to form this bond, and we're going to finally get to this point. That's going to be our final product. The hydrogen is going to go on the oxygen, and the rest of the alcohol molecule is going to attach itself right here. This is a hemiacetal. You might say, well, boy, that seems like a strange name. The equator cuts the Earth into two what? Hemispheres. So what is a hemisphere? A hemisphere is half of a sphere. Half. So hemi is a fancy way, or a fancy way of saying a half. Okay? So what does it, we've got, here is an acetal, but we're only halfway to the acetal. So it's a hemiacetal. It's half of an acetal. You say, well, that helps a lot. I never even knew what an acetal was. Now you know what half of one is. All right? This is real. But when we get to sugars, you're going to find that when sugars form a ring, this is how far they go. They form a hemiacetal. They stop right there. They stop midway. If you reacted the hemiacetal with another alcohol molecule, you get an acetal. I'm not going to dive into the details of that. But do know this. How does one alcohol react with an aldehyde or a ketone? When it's reacting with an aldehyde, you get an acetal. When it's reacting with a ketone, you get a ketal. Well, we get a hemiacetal with one, and we get a hemiketal if it's reacting with a ketone. All right, well, let's just take one more example. let's take propanol. Yeah, let's take a real molecule here. So we got propanol, and we're going to react it with ethanol. Ethanol. And I'll just write ethanol right down here. You got CH3, CH2OH is ethanol. So let's write it this way. Yeah, let's write it this way. All right, again, I'm just rearranging my ethanol in such a way that you can see what part of the ethanol is reacting with the aldehyde and where this is going to go. This is going to go here, and this is going to bind right here. And don't worry about naming these. Don't worry about naming these. You would be able to name these once we got into chapter 14, but so don't just worry about what the product would be. So let me move this over a little bit if I could. So we're going to get this. There's 3 carbons. We're going to get an OH where the carbon-oxygen double bond was. Here's the hydrogen. This here is the hydrogen that was right here. And so now this is what's left over here. That's going to bind right to there. All right, does that make sense? If you looked at this hydrogen and this portion of this, that's your original alcohol. It's the original alcohol. It's in a sense, I mean, it's a balanced equation. I didn't create anything new over there. I've just reacted these two together to form one molecule. Everything that was here is there. Nothing new. And that would be a hemiacetal. This would be a hemiacetal right here. Okay, so that's propanol with ethanol to form that hemiacetal. I hope you're seeing the analogy of things adding across a double bond. This is a very prolific thing a double bond can do. We saw the alkenes. You could hydrogenate them, halogenate them, hydrate them. You can hydrogenate a carbon-oxygen double bond, and now you can also react an alcohol with a carbon-oxygen double bond. These slides are just, I don't know, I can't follow that as easy as scratching things out in things. But there's your aldehyde, there's your alcohol, you're going to get a hemiacetal. So if those slides help you, fine. But I think it's a little clearer if we get these R's out of here and work with a real molecule. Yeah, these are just kind of going into the mechanism a little bit. How's this happening? Oh, this is the acetal. This is just happening again with the acetal, but don't worry about the acetal reaction too much. And I think these are the last 2 slides for chapter 13. This is summarizing the reactions. Yeah, so we've got oxidation of an aldehyde, get oxidation of an aldehyde. Oh, okay. Gets you carboxylic acid. Ketone, no reaction. The ketone is fully oxidized right there. Hydrogenation of an aldehyde gives you a primary alcohol. Hydrogenation of a ketone gives you a secondary alcohol. The aldehyde, you react an aldehyde with an alcohol, you get a hemiacetal. Ketone with an alcohol, you get a hemiketal. And then what you could put in here is that if you took a primary alcohol and oxidized it, that would be one way to make an aldehyde. If you took a secondary alcohol and oxidized it, you would form a ketone. So that would come under the category of how can I prepare an aldehyde? How can I make it a ketone? So there's a pretty good summary of reactions. And then this is probably a little earlier edition than your current book. All right, we ignored these reactions. So the keto-enol tautomerization, so don't worry about that. The aldol condensation, not that they aren't important reactions, but just the scope of things, we'll stick with this. Oxidation, addition of an alcohol, reduction. So main things are oxidation and reduction. Yeah, and you can kind of skip these. All right, any questions about 13? All right, so the homework on 13 would be due Monday. All right, let's shift over into chapter 14. I think we're actually getting a little bit ahead of schedule, but we also have this, we have the quiz at some point in time here in the future, and we have the class project, all right, October 23rd, Monday, over in CCC. Now, I'm not sure I mentioned to this class, there'll be a lot going on that day. It's mold day. It's going to be mold day. So there's going to be tables out on the patio. There's going to be other chemistry classes are doing demos, and different things are going on. So there'll be activities going on, and there'll be some advertisement for our presentation on sugar that will be right around the corner in CCC 121. So what you should be doing as teams is communicating with one another, finding information that relates to the portion of this topic that I've asked you to focus on, your team to focus on. So make sure you're on a team, you're communicating with the team, you're pulling information together, and someone on the team should be trying to gather that information into 3 or 4 or 5 PowerPoint slides that you would be able to present at that final thing. And also keep in mind that each team is not a standalone entity. What the intent is here is the 7 teams' information is going to kind of flow into a comprehensive look at what is sugar, how are we ingesting it, where is it coming from, is there more of this in our diet, what are the effects of it in our diet, that sort of thing, okay? So that it should flow through there from team 1 to team 7. It's telling a story. You may overlap. One team may say something, another team says similar thing. But, concentrate in the area I've given you. And if there is some overlap, that's fine. There's some things that need to be said more than once. Because really, I want the audience to walk away, and you. I'm going to have the class have some way of sitting back and listening to the whole thing and saying, oh, here's my 3 takeaways from what we said, from the information that was given, okay? And I want the audience, I'm not going to ask the audience to do that, but I'll be asking you to turn in something on, what are your 3 takeaways, and hopefully the audience will have maybe one overriding point that grabs them. Okay, is there any questions on that? So that's October 23rd. Is that about 3 weeks from now? 2.5 weeks from now? Maybe as we get a little closer, either the last class before the 23rd, so the Wednesday before that Monday, we'll try to get all the PowerPoints onto one memory stick sort of thing so that we can go up there and everybody's just working right through it. We'll put them in order from Team 1 to Team 7. All right, if anybody has any questions, feel free to ask me. Be talking about this with one another, kind of getting an idea of how we're going to do this. All right, let's move on to chapter 14. This will be a little bigger chapter than 13. I'm surprised at how fast we actually covered 13. I'm a bit surprised. I thought we had another full day's effort and knowledge, information on chapter 13. But chapter 14 is going to break up into 2 parts, carboxylic acids and esters. Esters are what we make from carboxylic acids. So let's get comfortable with what is a carboxylic acid, how to name them, how they react, and then that'll start moving us into esters. Okay, you are really familiar with carboxylic acids. I doubt anyone in here hasn't had vinegar. It is a carboxylic acid. It is a very simple one. This is acetic acid. That's acetic acid. Vinegar is 5% acetic acid, typically. Bottled vinegar on the shelf is about 5% acetic acid, 95% water. That's acetic acid. Sometimes you can go buy pickling vinegar. It might be 9% acetic acid. It's a little more concentrated for pickling purposes. But the general stuff that's going on salads is 5%, 95% water. And so you're seeing this carboxyl group. Carboxyl group. You probably won't see it written that way. You'll see it written that way more commonly than that. You rarely see it that way. A chemist probably doesn't like that because, if you don't notice that hydrogen right away, you think you're talking about carbon dioxide. This isn't carbon dioxide. It's carbon, oxygen, oxygen, hydrogen. So you have a carbon-oxygen double bond. You have an OH on the same carbon. So that's not an aldehyde and an alcohol. That's a carboxyl group. Acetic acid, lemons and citrus fruits, citric acid, apples, malic acid, citric acid. Whenever you see the word on a label, citrate, it might be sodium citrate. It's the sodium salt of that carboxylic acid, sodium citrate. It's a preservative, natural preservative. All right. Yeah, these are good. You can squeeze a little lemon juice over top of some things, and it won't brown or start looking like it's going bad very rapidly. It'll preserve it naturally. All right, among some of the first organic molecules that were studied. So some of these are just common names. This isn't an IUPAC naming system, it's just common names. All right, this is very polar. This is even more polar than alcohols. Yeah, you got an OH bond right here, which is a polar bond, but even more so, you have the electrons being pulled in this direction, and this becomes a acidic hydrogen. It can dissociate off of there in water. Well, let me just make sure you understand. If we take ethanol and put it in water, it dissolves. But what do you get? You just get ethanol in water. It does not dissociate. What's the pH of the water? It stays around 7. Doesn't make the water acidic. It dissolves in there, but this hydrogen stays on that oxygen. But if you take acetic acid and you put it in water, you're going to get somewhat of this ion and this ion. This is what we mean by an acidic hydrogen. It actually can dissociate off into the water, and so what happens to the pH? The pH is approximately 3. It drops. This is a weak acid. It's not a strong acid, which is why you can put it on your salad. All right? It doesn't, it's not hydrochloric acid, which would drop the pH to 1. It drops the pH to around 3. And your lettuce stays intact. With HCl, the HCl would chew up your lettuce before you got to it. And it would chew up your skin. Hydrochloric acid will react with the skin in an injurious manner, but acetic acid doesn't. Your skin can tolerate it. So we got a carbonyl and a hydroxyl group on the same carbon. We'll get into the naming of these. So here's a 3-carbon one. 1, 2, 3. Got the carboxyl group on the end. Here's the structural formula for what would be. So we're going to take propane, drop the E, and add OIC, and we get propanoic. Propanoic acid. This is the IUPAC name. This is the common name. Propionic acid. All right, I just said that it's actually more. Eric, can you turn this light out for a second? Let's remember I kind of usually draw a line down through these. And what you're seeing on this side of the line are just the carboxylic acid molecules. So if we had a container of pure acetic acid, not vinegar that's dissolved in water, just pure acetic acid, you could have hydrogen bonding here, hydrogen bonding here, hydrogen bonding from the carbon-oxygen double bond to a hydrogen on another carboxylic acid. There's lots of opportunities for hydrogen bonding between them. More opportunities than with an alcohol. This is about all you have with an alcohol, right here. But with a carboxylic acid, you have this, and because you're driving your electron, this electron here, into this area even stronger, the separation of charge is greater, and you get stronger hydrogen bonds. Now, if you put water in there, this is a polar molecule. Water's a polar molecule. Water can satisfy these hydrogen bonds just like a carboxylic acid molecule can. So you get water hydrogen bonding all around all of these here. Good solubility, better solubility than alcohols, and let's look at boiling points. So what do we have here? We've got the alkane. So again, I just like to kind of round these off. So we got about 0 degrees centigrade. Let's say 10. Here's our alcohol, around 100. Here is our aldehyde and ketone, approximately 50. So we're going from the alkane to the ether, aldehyde, ketone, alcohol. And look at this, is approximately 120 degrees centigrade. So 20 degrees higher boiling point, because these molecules are attracted to one another more tightly than even an alcohol of same molecular weight. So this takes the prize for the strongest hydrogen bonding right here, and the greater solubility in water. Both of those things would go hand in hand with that. That makes sense? We keep hitting on this. The molecules are tightly attracted to one another, being harder to boil, harder to get them to go into the vapor phase. Okay, nomenclature. IUPAC nomenclature, basically, is what I'm talking about here. Longest chain, go back to the alkane, it'd be butane. Drop the E and add OIC and acid. So we're going to call this butanoic acid. We don't just call it butanoic, it's butanoic acid. And we got a bromo group on carbon 3, so it's 3 bromo. Did I put the name on here? So this is 3 bromo butanoic acid. And just like the aldehyde, I don't particularly need a number here because it's going to be on the end. And it's saying here if there's 2 carboxyl groups, it's going to be a dioic acid. So if we had another one over here, it could be butane dioic acid. Butane dioic acid. Okay, so here's, I think I have a slide coming up that will show you the common ones. This is definitely one of them that you should know the IUPAC name. So here's the IUPAC name, 2 carbons, ethane, take off the E, we got ethanoic acid. It's more commonly and almost always referred to as acetic acid. Here's this ACET prefix referring to 2 carbons. Propanoic, propionic. All right, here's a dipic or hexane. You see here they left the E because we're putting dioic rather than have EIOIC, or having, so rather than having an N and a D next to each other, they've left the E, hexane dioic acid, or adipic. Malonic. Here is that, remember I showed you the alpha, beta, gamma. Here's an example of it. That would be beta-methylbutyric acid. I was just hearing something on a seminar I was listening to on the internet about memory and molecules that are good for memory, and they were mentioning butyric acid, not this molecule, but just straight butyric acid as a short chain very short chain fatty acid that is good for the nerves. I didn't get into all the details of why. All right, here's a slide you should really take note of. All of the ones that are in blue, you should, let's take these first four here. Well, here's where I could have made my comment about butyric acid right here. Methanoic, that's your IUPAC name, is also called formic. Anybody have trouble with fire ants? I think what did I do? No, I thought I heard at SAC someone had sat down and all bit fire ants. All right, well, here's the takeaway for you today. Here's what the ants are leaving behind when they bite you. They're leaving behind formic acid. All right? Bite you, and this is what they're releasing from their mouths, formic acid. So that's an acid. You can go in and get some baking soda, just get some baking soda, put it in a glass, a little water, stir it, and wipe that on the place where the fire ants bit you. And it will convert the formic acid into sodium formate. It'll neutralize the formic acid and take the sting away. So that's how you take the sting away from ant bites. If you're having trouble with them. Now, if you're on a picnic and forgot to bring your baking soda, I don't know what you do. But just throw baking soda in the picnic basket in case someone gets bitten. So there's formic acid, acetic acid, propanoic is propionic, butanoic is butyric. So this is the IUPAC name, butanoic. This is the common name. So if butter goes bad, stays out, gets rancid, it's forming some butyric acid in it. And it's coming from the Latin word for butter. Okay, we're going to look at these two molecules. I don't know what to say about this one. You can be aware of this one. These two, you should know the names and the formulas of those. We're going to take a look at those right now. These are fatty acids. Fatty acids. I was telling you that these are polar and generally have better solubility in water than alcohols. But these are going to get real long, 18 carbons long. And by the time you get that long, they are not soluble in water. Remember the alcohols, when they got 7 carbons long, they weren't soluble in water anymore. Well, here we're going to be up to 18 carbons long. This is why they are fatty acids. They're soluble in fat. They're lipids. They're lipids. They're not water soluble. Extremely important molecules in your body. Don't let anybody tell you fat is bad. We have gone overboard with that. You're starving your body for fat. Doesn't mean you have to have bacon every morning, but you do need omega-3 fatty acids is fat, okay? It's essential in your diet. We'll get back to those fatty acids in just a second. Citric acid, so here's your citrate. So this is in your citrus fruits, citric acid. So look at that, it has 3 carboxyl groups on it. Lactic acid in yogurt or in mussels. When you have, when you've exercised hard and actually you have not had, when you are exercising hard, your muscles aren't getting all the oxygen they need. So they go into anaerobic metabolism and they produce lactic acid. That's that muscle soreness. It's coming from this. Just a little interesting sidelight. Oh, isn't it right here? I think it comes up later. I was going to talk about polylactic acid, and I think it's on a later slide. All right, let's name some of these. Let's go ahead and name that top one. What's the parent name? Pentanoic. Pentanoic acid. It's going to be part of its name. Okay, there's a methyl on carbon 4. You start counting from the end of the carboxyl group, and you do count that carbon. That's carbon number 1, 2, 3, 4, 5. So you count that one, and then we have a 2-bromo, right? 2-bromo-4-methyl pentanoic acid. Okay, the second one, what's its parent name? What is it? Octanoic acid. If this is carbon 1, this is 2. This is 5 and 7. Two, 5, 7, what? Tribromo octanoic acid. All right, this one here, don't let this throw you. Just whenever you see a situation like this, just cover it and say, well, what would I call that? Cyclohexane, right? So now just convert that into the oic acid. Cyclohexanoic acid. Okay, now here we've got a benzene ring. So benzene is going to become benzoic. Well, both of these are just two ways of drawing it. These are benzoic acid. Well, you should definitely have this on a 3x5 card, plus those other ones on that other chart, that other slide there. Benzoic. There's another aromatic 6-membered ring that you're collecting this package of cards, this deck of cards. All right, let's mention the fatty acids. These were on this slide a few moments ago, right here. Right here, you see we've got oleic and stearic. So we're going to focus on these two. They're very similar. There's just one very important difference between them that you need to appreciate. All right, here is stearic. I don't know if you, let's see if I can make that a little bit bigger. Just notice here, that's a 16. So we got 16 of these CH2 groups. We got a methyl. We got a carboxyl group. So there's 16, 17, 18 carbons. Stearic acid has 18 carbons. Okay, notice down here, well, here it is right here. I don't have to draw it. There's your 16 CH2 groups and your methyl, your carboxyl. What they're showing here is if in the bloodstream at pH 7, generally, this proton will have left. And you've got a carboxylate anion here. You've got the H plus is floating around in the water. All right? Yeah, this is polar, even ionic. Very, very polar. But look how long that nonpolar tail is. It has a very long nonpolar tail. You kind of miss it if you draw it this way. This is showing you got this big portion of the molecule that has no polarity whatsoever, but it is stuck on this. So we got a molecule that has, and this is what makes it so interesting and so vital in the way it works in the body. We got a molecule that one end of it is water loving and the other end of it is hydrophobic, doesn't like water, doesn't want to have anything to do with water. And they're stuck on the same molecule. All right, now stearic acid is a saturated fatty acid. Saturated, no double bonds. Oleic acid, now you're getting this out of olive oil. We'll look at this a little bit more deeply in chapter 17. Just kind of what is in olive oil, what is olive oil, and what is lard and different things like that. But in olive oil is present this fatty acid, oleic, and there's one double bond right there. So it's mono unsaturated. This is a mono unsaturated fatty acid. Fatty acid. And not only is it monounsaturated, notice here you've got, well, here's your carboxyl group. This is wrong. That should be a 2. That's got a CH3 there. I don't know. I need to correct that. That should be a 2 right there. These are CH2 groups. CH2. 1, 2, 3, 4, 5, 6, 7. Then you get to the double bond. 1, 2, 3, 4, 5, 6, 7, and then you get to the methyl at the end. What's that tell you? The double bond is right in the middle, this molecule. And that is got physiological, biological implications to it. The molecule has a bend in it. Oh, the other thing here, cis. This is a cis double bond. Come in the double bond, you go back out the same side of it. You got a bend right there. Hence the no trans fats. Olive oil doesn't have any trans fats in it until you start cooking with it and heating it up real hot. You can produce some of that or oxidize it. It's a little more sensitive than stearic acid to heat and chemical degradation because this is a little more reactive bond right here. But in nature, olive oil is producing 100% cis double bonds. And that's really generally true for all of the fatty acids. Polyunsaturated ones, they're cis double bonds. Rarely find a trans double bond in nature. You find cis. All right, so be able to write these out, these formulas. Stearic acid, 18 carbons. Oleic acid, 18 carbons. But it has a double bond in the middle. Okay, I think a good place to start on Monday will be reactions in general. There'll be a couple simple ones we'll go through, just like what happens when you put them in water, and they are acids, they will react with a base, and then we'll start getting into deeper reactions like esterification and other things like that. Tell you what, I'm going to let you out a few minutes early. I mentioned the class project. Feel free to talk to one another on the way out. Let me kind of do two things at once. I'll try to multitask here. I'll call your name to give you this paper and take attendance at the same time. This is chapter 12 homework that some of you didn't pick up.